So different classes or types of acids have different pH curves. We're going to first look at the behavior of a strong monoprotic acid. On the graph you're producing in the lab, you'll be adding titrant, and so you're going to be going along this direction, and the machine we have back here, the device we have back here, keeps up with the volume of titrant automatically. All right? And then as the volume is increased of the titrant, that's the base solution, it's going to increase the pH. Okay? A strong monoprotic acid will have a beginning point somewhere down at the origin, down at close to 0. And it'll go like this, and then all of a sudden it'll start to turn upward like this. And then it'll go back over. And remember, pH goes from, some of you said the other day it was 1 to 14, but it's actually below 0. You can have a pH that's less than 0. Huh? No, I've never seen one go lower than, say, a negative 1.5, but it's possible, I suppose. But we're going to assume we're going to start at 0, okay? And 14 is maximum, and then 7 is right in the middle, right? 7 is what? pH of 7 means it's what? Neutral, okay. So a strong monoprotic acid will look something like this. Now, there could be some differences, okay? The slope here might be a little different on either end. That makes sense? But by and large, this is the general pattern you'll see of a strong monoprotic acid. All right? What does monoprotic mean? One hydrogen on the acid that comes off. Okay? So, hydrochloric acid is a strong monoprotic acid. If we put that in water in solution, all the hydrogen ions dissociate. Every single one of them, virtually anyway. Okay? Every one of them comes off. And that's just one hydrogen. Okay? Hydroiodic acid is a strong monoprotic acid. All of those come off. We only have one hydrogen that comes off. Alright? That's a strong monoprotic acid. Weak monoprotic acid. Weak monoprotic acids have a slightly different behavior. Usually, you can't get to 0 pH with a weak acid. Now, you need to know I've diluted all these acids just to kind of make it a little bit safer. So none of you are going to get to 0. You have to make some assumptions about where it would have started if it weren't diluted. Does that make sense? Everybody clear with that? Because 18 molar sulfuric acid is pretty dangerous. Okay, so I don't want you working with, what we're working with is pretty dangerous anyway, but I don't want you to have 18 molar, all right, or 15 molar acetic acid or something, all right? That's just a little bit too much for a high school college prep class. So you have to kind of make some assumptions about where this curve would have started if yours is a strong monoprotic acid. Got it? All right. A weak monoprotic acid isn't going to get to a pH of 0 in the first place. Typically, a weak acid looks like this in the beginning, okay? And you get this flat sort of, it's not quite completely flat. In fact, some of them go up like this a little more, all right? But you have this long stretch there. Remember that first lab we did where it took so much base to neutralize a weak acid? That's because of this region right here. And that's called the buffer region, okay? And then it'll turn up and slope over, okay? So the strong acid starts way down here and doesn't have, whatever you're going to call that. What do you call that? I don't know. Huh? It's almost a plane, but it's not quite because this never goes completely flat. And this line here never goes completely vertical. Close to it, but never completely vertical. Got it? All right. That's a weak monoprotic acid. Again, you got pH on this side. You got volume of titrant on this side. All right? Now, a strong, all right, thank you, diprotic acid, and what does diprotic mean? You got two hydrogens that come off, all right? Sulfuric acid is an example of a strong diprotic acid. And what happens is the first hydrogen comes off, just like with the weak acid, and I still have a hydrogen attached to that sulfate ion, and then that acid also will lose. This is also an acid. It's actually both an acid and a base, but this hydrogen will come off again, but you have to get the pH higher to get it to come off. So then this becomes a second, what we call a deprotonation. Okay, so we have two different hydrogens coming off at different points in the pH curve, in the process. Okay? So here's what this would look like. If it's strong, it's going to start down here at 0. You'll have that slope, just like kind of like before. But then something funky happens up here, and you have a second bump. You can call this a cliff face. And a cliff face right here is a cliff face. That's a plateau, if you want to. All right? I like to call it that because it's easier to discuss when you do that. So the strong diprotic acid starts out like a monoprotic acid, but then you got this extra bump where that second hydrogen comes off right up here. So this is where the first hydrogen is coming off. This is the second. Got that? All right, let's look at this weak diprotic acid then. So then a weak acid, remember when we looked at weak acids before, it never started down at 0 and you had this long plateau in the beginning. A weak diprotic acid starts out the same way. It doesn't start at 0. It'll do this. It'll go up, but you still have that second bump just like you had with a strong diprotic acid.
So the only difference between them two is the weak one doesn't start at 0?
Yeah. Pretty much. Now sometimes this second one gets kind of hard to see. It's not as pronounced as I made it here. I made it really pronounced to show you, but sometimes there's a little tiny little bump up there. You got to watch very, very carefully and be careful with your procedures. Got it? All right. And then we got triprotic acids. This is an example of a triprotic acid. There are no strong triprotic acids, by the way. Why not? That is a question that I don't think, well, I mean, there's a lot of high-level chemistry I go into, but really, did we want to go there today?
No, we don't.
Somebody on the last test didn't complete their mathematics work. This is supposed to be 2 negative up here on the sulfate's 2 negative. I don't know why I missed that. And so we've got 3 acids that are coming off this thing. 3 hydrogen acids that are coming off. Okay. All right, so a weak, yes. All right, a weak triprotic acid. So what do we know about weak acids, about how they start?
They don't start at 0.
They don't start at 0, they do this. Okay? And then there's your first hydrogen coming off. That's this equation right here. And you got the little plateau. Then you got a second hydrogen coming off, so there's another cliff face. And then the third hydrogen comes off up here. Okay? Does that make sense? 1, 2, 3 hydrogens coming off. Hydrogen ions. Now, these acids right here, I told you a while ago, sometimes the second bump on a weak diprotic acid is really hard to see. This one is even harder to see. It might not even show up on your graph at all.
So then how do we know it's there?
It's kind of hard to tell. We could have the computer do what's called a derivative, and we might be able to see it. Okay? That's calculus, by the way. So one of the important reasons for taking calculus is you understand what's going on when you do those kind of things. Because this bump can be so small, you might just look like, garbage in the graph. Might not make any sense. But if we were to do a second derivative of this graph, we might actually see that. We might be able to find where that is. Sometimes you can do it that way. You can have really, really sensitive equipment and go really, really, really slow, which we don't have time to do, right? Because we've got just an hour and a half in this class. We're spending part of it talking about theory, okay? So you're going to have to look very, very carefully, especially on the back end of it. And be patient, because some of the stuff, you like nothing's happening. All right? Yes?
On the last one, you said 2 or 3.
Right. 3 negative here. That's a 2 negative. This is a 3 negative here. Phosphate has a 3 negative charge. And that's what you're ending up with at the very end, when everything's completely titrated. So what's happening here in all these graphs is that as you add base, you're starting out with a really strong acid, or really as concentrated as we can, where almost none of the hydrogens have come off, and we're ripping them off with the base. Okay? Pulling those hydrogen ions off of the acid by adding base to the solution. That's one way to think about it. You with me? All right? Now, are you ready to get started?
I'm born ready.
Born ready, he says. All right. So, I'm letting you self-select your groups because this is the last lab. You have to have been all 3 lab officers by this time, and you can't be 2 lab officers in the same lab. Okay? Anybody have any questions? Well, let's get started. We've got a lot to do.
You gotta look at things, don't you?
I'm going to check them in the lab. I'll come back down and look at what you got.